Hi, my name is Jonathan Cohn, and I'm a fifth-year grad student working with Janelle Walsh at Texas A&M. My talk is about making a gas-dynamical black hole mass measurement for the local compact galaxy UGC 2698. So there are three main methods to directly measure black hole masses, which involve modeling the observed kinematics of stars, nuclear gas disks, and water megamaser disks in active galaxies. Recently, molecular gas dynamics have been revolutionized by ALMA, which has much higher resolution and sensitivity than previous millimeter-sub-millimeter observatories. As a result, there's been a significant increase in the number of gas-dynamical black hole mass measurements. Now, we know that black hole masses correlate with bulge properties of their host galaxies, such as the velocity dispersion as shown at right, despite the fact that these bulge properties extend well beyond the black hole sphere of influence. So to improve our understanding of these relations, we need more robust, precise black hole masses and more masses at the high and low mass ends. So we recently identified a population of local compact galaxies with high velocity dispersions, expected to have high mass black holes. In contrast to the large, round, dispersion-supported galaxies that usually have such large black holes, these galaxies are disky, rotating, and very compact. In the size versus mass figure at left, these local compact galaxies follow the redshift 2 relation, even though they exist around redshift 0. They have uniform old stellar ages and no evidence for major merging since redshift 2, indicating that they may be passively evolved relics of redshift 2 red nuggets. And so far, we have stellar dynamical mass measurements for 3 of the galaxies in this sample. Interestingly, we found their black holes lie on the M-sigma relation, but we find them to be overmassive on the mass-luminosity relation shown at right. Now, how might you get galaxies like this? The left panel of this cartoon shows how we think galaxies with large black holes might normally grow. They build their stellar core and black hole mass up to redshift 2, after which they grow mainly via mergers that add stellar mass, primarily to the galaxy outskirts. And if that's the case, then some redshift 2 red nuggets, now shown at right, may just not go through the mergers necessary to increase their size after redshift 2, leaving them as compact galaxies with overmassive black holes on the black hole mass bulge luminosity relation. So we found that about half of the local compact galaxies in our sample exhibit regular dust disks in HST I-band images. So we obtained ALMA observations of a few of these galaxies, including UGC 2698, shown here, at a resolution that would just resolve the expected black hole sphere of influence, testing for the presence of regularly rotating molecular gas. And indeed, we find a well-ordered rotating CO disk, as shown in the map at right. So based on these data, we construct our gas dynamical model, assuming that the gas follows circular orbits in a thin disk. We determine the circular velocity based on the enclosed mass, which depends on the black hole mass, the stellar light distribution, and a mass-to-light ratio. The model velocity is then generated on a subsampled grid and projected onto the sky with inclination. And then we assume that the intrinsic line profiles are Gaussian, centered at the line of sight velocity at each point in the grid, and with an intrinsic width equal to a turbulent velocity dispersion. Then, after bending to the original pixel scale, we convolve the model cube with the ALMA beam and compare the resultant model to the data. Our model contains 9 free parameters, including the black hole mass, and we use Dynasty, a nested sampling code, to optimize the free parameters. So we find a best fit black hole mass in UGC 2698 of 2.46 billion solar masses. In the image at right, I compare the best fit model line profiles in blue to the data in black at 4 example locations in the gas disk, showing that our model is a pretty good fit. The statistical errors on the black hole mass shown in the figure at the bottom left are very small. But we also test a range of different models to determine the systematic uncertainties which dominate our error budget at about 0.7 billion solar masses. So now we can place UGC 2698 on the black hole scaling relations. Shown at left is the black hole mass bulge velocity dispersion relation, and at right is the black hole mass bulge luminosity relation. And unlike the 3 compact galaxies for which we already have stellar dynamical black hole masses, our gas dynamical black hole mass for UGC 2698, shown here as the blue diamond, appears to be consistent with both scaling relations. So now we have 2 possible explanations for this. UGC 2698 is actually the largest in both mass and radius of our local compact galaxy sample, with some evidence for stellar growth in its outer regions. So it's still possible that these galaxies are relics, and UGC 2698 may have experienced a bit more growth than the rest of the sample, bringing it more in line with local black hole scaling relations. Alternatively, there could be more intrinsic scattering the scaling relations than currently thought, and the overmassive black holes could just be somewhat unusual cases. So to get a better understanding of the intrinsic scatter, we need more black hole measurements made with independent methods at the high mass end of the scaling relations. So to conclude, we perform molecular gas dynamical modeling to measure the mass of the black hole in the local compact galaxy UGC 2698. We find a black hole mass of 2.46 billion solar masses, which is consistent with the black hole scaling relations. Moving forward, we'll make gas dynamical black hole mass measurements for more galaxies in the local compact sample, which will help us further explore whether black hole growth may precede the growth of stars and galaxies, or if the high mass end of the black hole scaling relations may just have more intrinsic scatter than previously thought. Thank you.